Today we will solve the problem 3.6 and 3.7 of Griffiths third edition Introduction to Quantum Mechanics. Problem 3.6 is consider the operator Q capital Q cat which is equal to T2 over T pi 2. That is this is a second order derivative with respect to pi. Where as in example 3.1, don't worry about that example, pi is the azimuthal angle in polar coordinate and functions are subject to equation 3.26 is operator q is Hermitian, then point its eigenfunctions and eigenvalues. What is the spectrum of operator q? Is the spectrum degenerate? Here, the equation 3.6 gives you that f, some arbitrary function f, uh, which is function of pi with 2 pi, is exactly same as pi. Say, for example, you have a circle, then you select a point here and start with after rotating 2 pi degree, you will reach the same point again. That is the idea behind this expression. Now we will go to the problem. We will check the hermicity of the operator Q. Let Q act on get vector G. Take the inner product with the F. So in the integral form, it will become the integral 0 to 2 pi F star T2 over T pi 2 G because this operator is T2 over T pi 2. So integration is with respect to T pi. So you do the integration by part. So this can be taken as a UV method. U is F star, V is first order derivative of G with respect to pi. So this will become F star Tg over T pi between the limit 0 to 2 pi minus V du. V is here, V is Tg over T pi. Tu is this uh, F, F star over T pi. So it is convention that we will always write the complex function first, then uh, complex number first, then the other functions. So, which is equal to here, if you apply the limit, uh, periodic limit 0 to 2 pi, at periodic boundary, this term will become 0. So, you will get only the second term, that is uh, B du. So U is F star. So du is Tf star over T pi. So we will get only the second term. First term will get cancelled. Now you do again this integral by parts. Here you take as G as V. This is as Tf over T pi is U. This is V. Then this will become minus, because already there is a negative sign, minus Tf star over T pi G between limit 0 to 2 pi, and minus of minus will become plus 0 to 2 pi. uh, then you will get V du. So V du, that is here U is first order derivative of f with respect to pi. So if we take again the derivative, this will become second order derivative integrating with respect to t pi. Then as usual, as a convention, you take complex value first, complex function first. So you bring this g next. So this will be uh, this is operator. remember that T2 over T by 2 is operator. So that operator act on the bra F, and this is get G. So look at here, we started with bra F get QG. We end up with bra QF and get G. By swapping this operator, your result does not change. So we have confirmed the Hermicity. That is F Q cat G is equal to the inner product of Q cat F with G. So we have proved the Hermicity. Now our next task is we have to find the eigenfunction and eigenvalue. Let us take the operator Q act on F. So we will get the eigenvalue Q, and it is multiplied by this function F. Now, if you take second order derivative, uh, that is here, Q is, we are replacing Q by its operator, which is T2 over T by 2 F, which is equal to QF according to this our text. So naturally, this solution for this one is F plus or minus is equal to A e power plus or minus square root of Q into pi. According to our periodic condition, square root of Q into 2 pi must be equal to integer multiplied by this 2 pi and I, or this 2 pi and 2 pi will get cancelled. So square root of Q is equal to IN. That means we take square, Q is equal to I square is minus 1, this N square. So naturally, this is a doubly degenerate because it will have both positive value as well as negative value. So it is doubly degenerate except for n is equal to 0, and the type of spectrum is, you can see this is the exponential one. So now we have answered all the questions. Then problem 3.7 part A. Suppose that f of x and g of x are two eigenfunctions of an operator q with the same eigenvalue q. So remember that it has same eigenvalue q. So that any linear combination of f and g is itself an eigenfunction of q with eigenvalue q, here capital Q, operator q. And next is check f of x is equal to e power x and g of x is equal to e power minus x are the eigenfunctions of operator t2 over tx2 with the same eigenvalue. Construct two linear combination of f and g that are orthogonal eigenfunction on the interval -1 to +1. So first we will address the part A, section A. That is, suppose uh, it is given that eigenvalue is q for both f of x and g of x. So when q act on f, you will get an eigenvalue q and multiplied by this function f. And if it act on G, you will get eigenvalue Q, and which is multiplied by G. Let us take a linear combination of this F and G. Uh, that function you call it as h of x, which is equal to a times f of x and plus p times g of x. We are taking linear combination where a and b are two arbitrary constant. Now, let us say that the operator q cat act on h, then you will get it is equal to q operating on this af plus bg. Now, Q naturally is a linear operator. We can write this as A is a constant, you take it front, then this will become q cat f. Similarly, for the second term, p you take out, and this will away q cat g. By definition, qf is equal to small qf from this definition, and qg is small qg. So now q is an eigenvalue. So you take q, both first and second term contain q. So you take q outside, then this will become, first term will become af, second term will become pg, which is nothing but these terms inside the bracket is nothing but h of x by definition we have taken. So naturally, the this will be equal to q into h of x. That is the linear combination of the eigenvalue part is a linear combination. We have taken a and b arbitrary constant is equal to q h of x. So we are getting the same eigenvalue. So any linear combination of this f and g will have same eigenvalue. Now we will check the orthogonality of this problem. That is, it is given in the problem f of x is equal to e power x, which implies that the first order derivative of f of x is equal to e power x. Then if you differentiate x with respect to x, you will get plus 1. If you take second order derivative, same thing, e power x, again it is if you differentiate x, you will get 1. So here the value is 1 into e power x. Where e power x, e power x is f of x in this case. Similarly, you take g of x is equal to e power minus x. You do the same thing. If you take first order derivative, here only this small difference. You will get with respect to x, if you differentiate with respect to x, then you will get minus 1. You again, if you take second order derivative, minus 1 into minus 1 become plus 1. Here you can see e power minus x is equal to g of x. So here T2 over Tx2 is an operator. So when operator act on f of x, you will get eigenvalue 1. Same is the case here also. Here g of x, if you differentiate, you will get same eigenvalue 1. Both the cases you are getting eigenvalue 1. That is here also 1, here also 1. So in both cases, yeah, when operator act on f of x or g of x, you will get same eigenvalue 1. So now that is not a problem. Now we will check the simplest orthogonal linear combination. So the simplest orthogonal linear combination are f of x is equal to, we will define a function capital F is, which is equal to addition of these two, e power x plus e power minus x. Let us take g, another function, that linear combination is equal to e power x minus e power minus x. You can take other way around also, that is minus e power x plus e power minus x. But both case you will get same result. Here the coefficient is C1, C2. We have taken here C1, C2 as 1, 1. Here C1, C2 as 1 minus 1. Now you take the inner product of capital F with capital G. Then you take this function and this function. What you will get? You multiply the integral limit as per the problem. The limit is given between minus 1 to plus 1. So you multiply both. So power x into e power x, you will get e power 2x. E power x minus e power x. So you remember that there is a negative sign. So that is minus e power x into e power minus x. Next you take e power minus x. So e power minus x into e power x, e power minus x into e power x. Then you multiply these two. So that is here you have minus. So this will become minus e power minus 2x. You are integrating with respect to dx. Now you look at the second and third term. Both are equal and opposite sign. So you can cancel these two. So this will become 0. Now, first and last term only left out. So we are taken that integral minus 1 to plus 1 e power 2x minus e power minus 2x. So if you differentiate this, sorry, if you integrate this, you will get 1 over 2. Both cases you will get 1 over 2. So I have taken 1 over 2 outside. Then within the bracket, this is e power 2x. Here you can see here is a minus, and when you integrate integrate this minus 2, you will get minus 2x, you will get 1 over minus 2. So this minus and this minus will become plus plus e power minus 2x. So you have to apply the limit minus 1 to plus 1. If you apply the upper limit in the both cases, this is upper limit is 1. So e squared plus e power minus 2 here. And if you apply the lower limit, that is minus 1, this is minus e power minus 2, and this is also e power uh, minus of minus 2 will become plus 2. So minus e plus e power plus 2. Here it is when you apply lower limit, this x is minus 1. So naturally that is e power minus 2. Now we can see these terms. You first look at the term. These two terms will get cancelled. That is e squared will get cancelled with this minus e squared. So this will cut. And second and third term, if you look at, both are equal and opposite sign. So both will get cancelled. These two will get cancelled. So net result is you will get 0. So we have proved the orthogonality of any linear combination of these functions. Thank you very much for watching my videos and supporting me continuously. Thank you very much.